My name is Taisuke Boku from University of Tsukuba, and I'm the director of Center for Computational Sciences, which is a supercomputer center in our university. So first, I'd like to briefly introduce our center. So Center for Computational Sciences, or CCS for short, were established about 28 years ago. And at first, we were established as a Center for Computational Physics. But after 12 years of the operation, it's enlarged to the computational sciences. And there are 43 faculty staffs today, and about 2/3 of them are from application scientists. And while there are another 1/3, including me, is from the computer science field. So this is a very good collaboration field in the both needs of the domain scientist and the seeds of the computer scientists work together. And we are also one of the national supercomputer centers under MEXT. MEXT is the Ministry of Education, but we are only one research center, and because all other national university supercomputer centers are established as a service centers. But we have a very good team of the research itself for the computational science and computer science. So the history of the University of Tsukuba for the development of the supercomputer is very long. It's more than 40 years, but the first one is a very small, only 9 8-bit microprocessor, started from the 1977. And after the 1992, we made our center, and the first one was named CP-PACS, and it is a memorial system because in the November 1996, we got the #1 in the top 500 list at the time. So that is a biggest history of us, and we continue to make some sustainable development of the very good experience with computational scientists and the computer scientists so far. So there are 3 programs to share our center. So since our center is marked as a one of the national supercomputer centers, so we accept all kind of the project from the computational science field. And the main part of the program in our center is called the MCRP, which stands for the Multidisciplinary Cooperative Research Program. And we provide about 50% of the every year's node hour of our supercomputers, and perfectly free. So it means that the CCS covers all the node hour. It is very gorgeous for users. And of course, the projects are peer reviewed by our CCS and also the external committee. And HPCI is the second one, which stands for the High Performance Computing Infrastructure. So that is a nationwide program by MEXT. And all the Japanese national supercomputers are under the umbrella of the HPCI. And I'm actually, I'm now the president of the HPCI consortium. So in our center, we provide about 30% of our node hour, also for free for users. But actually, this part is covered by the MEXT and peer reviewed by the HPCI consortium and the project review committee. And in this 2020, we especially add some special program under the COVID-19 attacking, and there are so far 18 projects are accepted, and 5 of them using our CCS supercomputers. And the last one is a general use, that is a paid node hour computation by anyone in Japan, and we provide about 20% of our resources. So MCRP in last year, 2019, we accepted 78 projects and over 600 users for 2 supercomputers. I will show later about the computer. And we contributed more than 400 of the technical papers for the researchers. So out of 2 supercomputers, first one is Oakforest-PACS, or OFP for short. So actually, this machine is a joint machine with the University of Tsukuba and the University of Tokyo. And we paid some part of the system procurement and also managing everything to get together under collaboration of two universities. And the machine is very gigantic, and so with 4 megawatt of the power consumption. So this machine is not in our center, but then placed in the Kashiwa campus of the University of Tokyo, which is very close to our center. So it is 8,208 kernel CPUs. It has been running for almost 4 years so far. And we have 25 petaflops peak and 13.55 petaflops of impact benchmark. So at the first appearance in the November 2016, it was ranked as a number 6, just after the NASC Cori system as a number 5. And of course, we were number 1 in Japan, exceeding the previous record of the K computer. And we also have a 25 petabyte of the DDN raster HDD, plus 1 petabyte of the burst buffer SSD, also by DDN. And currently it is ranked as a number 1 in IO 500 bandwidth. And installation is done by Fujitsu. So the machine has already 4 years old, and we will run this machine another 1.5 years, then shut down, and we will make a new procurement, hopefully running starting with at the early 2023. I'm sorry. So it is temporarily called the post OFP, but the name is not decided yet. And finally, this is the first appearance. This was the largest cluster of the kernel plus OmniPath. Oh, by the way, so the name for the Oak Forest came from the University of Tokyo's convention, and the PACS came from our convention. So please don't call it just Oak Forest. Oak Forest-PACS is the correct name. The second machine, just owned by our own, and it is called Cygnus. So this is today's main topic. So Cygnus is the series name PACS 10. And this is the world's first supercomputer with a multi-hybrid. It means that GPU plus FPGA working together in the same node with such a very complicated accelerating architecture. So there are several systems by the FPGA, but I think that this is only one as a practical and the production level of the FPGA-based cluster. And also we combined the GPU plus FPGA together. So that is a very, very unique system. And this is a picture of the single node. And as you see on the left side, there are 2 Xeon CPU, Xeon Gold, and we employ the 4 NVIDIA Volta V100 PCI Express version, plus 2 Intel Strategic STEM-based FPGA boards. So it is really heavy, and one node has about 30 teraflops of the peak performance. And on the back side, we have InfiniBand HDR 100 by 4 channel to support the 4 Volta V100 GPUs. And it is combined into the HDR 200 InfiniBand Mellanox switch. And on the other hand, on the FPGA, each FPGA card of the Strategic 10 is equipped with 4 channel of the 100 Gbps optical link. So it is also a very fast interconnection between the FPGAs. And finally, there is an HDR 200 Mellanox switch here. So Cygnus is, as you know, this is the name of the constellation. So in the Cygnus constellation, there are 2 big stars. One is the Deneb, and the other one is Albireo. So Deneb is the alpha star, and the largest part of the Cygnus system is configured as a Deneb style node. I will show later. And the second largest part is called Albireo. So Albireo is actually the double star in the Cygnus constellation. So we symbolically named this part as Albireo because we have a GPU and FPGA double accelerator. So we named this part as Albireo. So Albireo style of the node is something like this. So in one node, we have 2 Xeon Gold CPU and 4 Volta 100 GPUs, plus 2 of the Intel Strategic 10 FPGA. And also the InfiniBand HDR 100 by 4 such a very, very gorgeous node architecture. And while the Albireo is a double accelerator configuration, so Deneb part is only with Volta, no FPGA. But it is an identical. If we insert an additional card of the FPGA, it can be changed to the Albireo architecture. So this is a specification of the Cygnus system. So this is, it has only 81 nodes. It is not so gigantic system. And we have 2.4 petaflops double precision, mainly by the Volta GPU, plus 1.6 petaflops in impact. So the machine is relatively small, but as I told, so it is very unique architecture with a combination of the GPU plus FPGA. And how to use the FPGA is a really big problem, and I will introduce briefly later. Also, each node has an Intel NVMe 1.6 terabyte and DDN raster system and the Mellanox InfiniBand switch. And the system integrator is NEC. So there are two kinds of the network interconnection in the Cygnus system. The entire system is connected by the InfiniBand HDR 100 and 200 combination, as the ordinary cluster system. It is a full bisection bandwidth of the FAT3 network. But for the FPGA, they have their own individual network with a 2D torus. So since we have 32 nodes of the Albireo type, or 64 FPGAs, so all these 64 FPGAs are connected by 8 by 8 2D torus. And of course, an FPGA and an optical link doesn't work without any special hardware supporting software system and also the programming system. So we developed our own network system for the connection of the FPGA. So why we introduced a multi-hybrid? So everyone knows that the GPU is a very, very good and accelerating technology, but some part of the computation or some sort of the computation is not good at for the GPU computation. For example, in some part of the big code, the parallelism is shrink to very small amount of the parallelism, and the FPGA is a pipelining system, so there is no bottleneck of the, even with a small degree of the parallelism. While the GPU is a SIMD, very large scale SIMD, and it doesn't work well for such a situation. And also, if there are many of the if then else branches, GPU doesn't work because it is a SIMD device, and so on. And most importantly, GPU has its own interconnection. So that is a big difference from GPU. So FPGA has a 4-channel of the 100 Gbps. That is the most advanced optical network. So our idea is that many of the very complicated physical simulation consists of the multiple phenomena. So each phenomena is, some phenomena is good for the GPU and someone is good for the FPGA and so on. So we think that in the strong scaling by the Amdahl's law, these last part is a bottleneck of the computation. So we have 2 devices. So we developed a couple of underlying technologies. The most important one is FPGA to FPGA communication. And we like to open the system to the application users. So usually the FPGA is programmed by the Verilog HDL or some lower level hardware description language. But then to enable the users to write the OpenCL code for their communication between FPGA, we developed a special system named CIRCUS. So CIRCUS stands for the Communication Integrated Reconfigurable Computing System. And here we perfectly combine all the pipeline of the communication and computation seamlessly. So we could get a very good performance throughput. So this is a sample code of the OpenCL level of the CIRCUS. And here, right channel Intel is a communication channel from the OpenCL to underlying Verilog HDL modules. And we made such a module by the Verilog HDL, and the users just enjoy the communication with very, very fine-grained size. And this is a performance graph, and in the left side, you can see that then out of 100 Gbps physical performance, we could achieve 90 Gbps, so the 90%. So it's depending on the hop count because it is a 2D torus. But finally, in any distance, we could achieve 90% of the peak performance. And the right side is latency, but I will skip this one. So another problem is how to combine the GPU and the FPGA. And of course, they are connected by the PCI Express. So it is possible to transfer the data through the CPU. But we developed a direct DMA module for the FPGA, which can kick the data transfer between GPU and FPGA completely only by the FPGA. So after the first initial setting, so CPU doesn't care about the communication, and the two devices can perfectly communicate. And it is also available from the OpenCL. And this graph shows the throughput of the GPU FPGA DMA. So the purple line shows the previous traditional way through the CPU. And this is GPU to FPGA, and this is the FPGA to GPU. So since the FPGA is controlling everything, so this direction is much faster than the reading out from the GPU. But anyway, it reaches to the almost peak performance of the PCI Express. And most importantly, the latency is very small. So for the FPGA to GPU communication, it takes only 0.6 microsecond for the DMA. Okay, so finally, I like to show one example of the application. So it is an early universe simulation, which is called ARGOT. ARGOT is developed by our centers, University Astrophysics part, and we collaborated to implement the very two phenomena. So one phenomenon is done by the GPU, and the other one is done by the FPGA. Because this ART part is not good at for the GPU computation, so we implemented it on the FPGA. So after the performance evaluation with, this is just a single node without any communication by the FPGA. But coupling the GPU plus FPGA together, we could achieve up to 17 times faster speed up. So when the problem size is very small, the GPU doesn't work well, and the FPGA can tolerate such a problem of the GPU. So it is a tremendously fast speed up 17 times with only coupling of the GPU plus FPGA. And when the number of the problem size increased, the GPU is getting better. But then with the largest size, which allows on the memory, still we have 1.3 times faster speed. So that's it from me. So the Cygnus system is a very new style of the double accelerator system. So if you are interested into the system, we are ready for the collaboration for anyone in us. Thank you very much.